Greetings everyone, I am Vitojit and it is a privilege for me to be able to share my work on approximate ternary quantum error correcting code here at the prestigious ISMVL. Uh, so what we'll do is we'll quickly go through the introduction and then we'll come to the encoding and the motivation of our work here, the encoding system of the error correcting code, and then we'll move to the specific correcting techniques for the different errors as well as the circuit representation of this. So coming to a quantum system, this is a physical representation of a qubit. This is an enharmonic oscillator, the energy spectrums of those, and the lower energy spectrum, the lowest one is represented as a 0, the immediate higher as a 1, but we see that further higher levels exist. So we have here 2, 3, 4 and so on. And therefore a quantum system is inherently multivalued. Now, why should we move to multi-valued system? Well, there are many reasons. The first is as we move to higher dimensional system, the search space increases. And this has some excellent applications in quantum cryptography, quantum random walk algorithms, and then we have faster training of machine learning, etc. Now, why focus on ternary then? The focus is on ternary because it has been shown already that there are some gates which are called the MS gates. I'll elaborate these later actually, which can be actually implemented in ion trap. So this is not all just theory, it can be actually implemented in the laboratory. But there are some disadvantages of multi-valued systems as well. So the disadvantages are the circuit cost increases and the system becomes more prone to errors. It becomes more difficult to control in the laboratory. So our goal here is that we want to design some quantum error correcting codes for ternary systems so that they are the codes are compact, the circuits are compact, the number of qubits requirement is small and the circuit cost is low. Now, noise can affect a system in different ways. So I have represented this using qubits. These are block spheres. It is simply because it is easy to represent. So a block sphere, this is a 0 qubit and an error acts on it such that the state is changed somewhat. So it is an unwanted operator. But the action of noise can be actually mathematically represented in multiple ways. We'll focus on the depolarizing noise model, but quickly to elaborate, the amplitude damping actually captures those type of systems which are already in higher energy states, but they spontaneously decay to the ground energy. And the phase damping system is something like the system spontaneously acquires some unwanted phase amongst the basis states. But for depolarizing noise model, these can be represented as unwanted unitary operators, and Peter Shaw showed that such an error operator can be written down as a linear combination of these Pauli matrices. So this identity sigma x, sigma y and sigma z, these are called error Pauli matrices. Extended it to the ternary system, the depolarizing noise model looks something like this. So here this x is corresponding to sigma x, z corresponds to sigma z, and y corresponds to sigma y. The action of z is simply that it gives some relative phase to the basis states, and the action of x is that it changes the basis states. So 0 goes to 1, 1 goes to 2, 2 goes to 0 and so on. And y is simply both of these errors taken together. Now, if there are errors, we require some techniques for correcting the errors, and any natural technique of error correction requires that a small number of qutrits are encoded to some higher number of qutrits. Now, this has some penalty. First and foremost, it reduces or it actually slows down the computing because some significant amount of time is gone for correcting errors. And then it reduces the effective number of qtrits, because if we have a n many qtrit system, then we are down to a smaller number of error corrected qtrits. And the QECC blocks themselves, they are not fault free. So they may introduce further errors in the system, making the system even worse. Now, coming to this stabilizer formulation, this is a high level way to look at error correction. And again, initially I will come to qubit because it's easier to represent. Suppose we have a qubit like this, which is encoded in this form called psi. And this Pauli operator sigma z, the action of sigma z is that it acts on 0, it gives a +1 eigenstate, and on 1, it gives a -1 eigenstate. Now we'll say an operator S, which is created from these Pauli operators, is a stabilizer for this code word shy if it gives a +1 eigenstate for the code word shy. But whenever an error occurs, this E, the stabilizer should act on it to give a -1 eigenstate. And the stabilizers themselves should commute. That means that you can operate them in any order you want. So here is an example. Suppose that this state there is a bit flip error has occurred. The first Q bit has actually changed, and these are the two stabilizers. You can see this one has become -1. So just by looking at the eigenvalues, we can identify which error has occurred. So naturally the ternary stabilizers, so these were the operators that we have shown earlier. So the ternary stabilizers will be formed from these operators. We have already seen the action of these. The only difference will be here on error state, the eigenvalues will be either omega or omega square. Now the motivation for this is that we want CSS type QECCs. So a CSS type QECC is where we can partition the set of stabilizers into two parts. This contains only this X type of operators and this contains only the Z type of operators. Now why this is important? Because if we have something like this, then this type of thing can correct a phase error, this can correct a bit error, and if these errors occur on to different qtrits, then simultaneously two of them can be corrected. And it has been shown in some papers that CSS codes have lower circuit cost compared to non-CSS codes, and the 7-qubit code, the STEAM code, is the minimum for binary. And one more definition is that we say that a QECC is degenerate if there are two different errors, two or more different errors, such that they acting on the code word gives the same error state. Now there are two results that has been shown that if we build a degenerate QECC and a CSS type one, then the minimum that we can do is requires 6 qubits. And again, another research shows that there does not exist a 6 qubit QECC unless you have the encoder and decoder sharing some external entanglement. So we ask the question here that we don't want to share this external entanglement. We want 6 qubits and we want the CSS structure. What is the best we can do? We cannot reach perfection because of these results, but how much approximation can we reach? So this is our goal here. This is our encoding scheme. So this qtrit is encoded into this logical qtrit where the 0 logical is something like this, and similarly we'll have 1 logical and 2 logical. The x1, x2 will call bit error. These are the phase errors, and y are taken together. Now these two are the stabilizers for phase error correction. So if you see, the first stabilizer operates on Q1, Q3 and Q5 only, and this operates on Q0, Q2 and Q4 only. So we can say that these two stabilizers kind of partitions the qtrits into these two sets G1 and G2. Now if a phase error occurs on one of the qtrits of G1, then this will have a non-unity eigenvalue, and if it occurs on somewhere here, then this will have a non-unity eigenvalue. But if at any point we find that both of these stabilizers have non-unity eigenvalue, that means there is a phase error here and here as well. So this type of simultaneous phase errors we can correct. One phase error here and one phase error here. Now let us focus on one of these sets only. Let's focus on G1. So we have a single phase error Z1 acting on these qtrits of G1. These are the three qtrits, and we can see that these are the stabilizer outcomes. So it's a degenerate code, and the Q3 and Q5 phase errors on Q3 and Q5 actually acts in the same way. So it doesn't matter which one we correct. Now what happens if more than one of these qtrits will incur phase errors? Let's see that. Let's suppose two phase errors has occurred. So these are the possibilities, and we see that if Q1 and Q3, Q1 and Q5, they have phase errors, then these phase errors effectively cancel each other out. So effectively we have no error. And Q3 and Q5, the phase error behaves same as a single phase error on Q1. So we can actually see these stabilizer and we can think that phase error on Q1 has occurred and correct it. Similarly, we can work out that 3 simultaneous phase errors can be corrected as well. So what we have, we can extend this to G2 equivalently, it's exactly the same. So what we have is that up to 3 simultaneous phase errors can be corrected in each of these sets. So, and we have already argued that phase errors on 2 of these sets simultaneously can be corrected. So we have this verdict that up to 6 simultaneous phase errors we can correct on this code word. Fine. Now we are also interested in the circuit of this because we want low cost circuits, and for that we use this MS gates or multiplication and Stroud gates that can be implemented in ion traps. So these are some of these gates. These are single qutrit gates and these are two qutrit control gates. And multiplication and Stroud showed that this can be implemented in ion trap. And another type of gate is this extension gate, which is basically the extension of Hadamard gate in the ternary system. What it does is it takes the X operator and converts it to Z operator, and vice versa. It takes the Z operator and converts it to X operator. So what we'll be interested in that the cost of our circuit will be measured in terms of these MS gates and extension gates. Fine. So this is the circuit for phase error corrections. And you can see that each of these X1 actually corresponds to what we call this C plus P gate. So what the C plus P gate does simply is that the control remains unchanged and the target is basically a summation of the control and the target. So this is what is written down here. Each of this X1 corresponds to a single C plus P gate and X2 is basically X1 taken twice. So that is basically 2 C plus P gates. Now this C plus P gate is not an MS gate, but it can be generated using 3 MS gates like this. So the cost of each C plus P gate is actually 3. Now correction of bit errors, here these are our stabilizers, and here we show that for Q2 and Q3 the stabilizers give the same outcome. So what our conclusion here is that it can correct bit error perfectly for Q0, Q1, Q4 and Q5. For Q2 and Q3, it can detect that some error has occurred. It has occurred on either Q2 or Q3, but it cannot identify on which Q3 the error has occurred. And this is where the approximation comes in. We have already seen that we cannot expect to get a perfect error correcting code using 6 qtrits since we are not sharing any external entanglement. And this is the source of approximation. Now the circuit for bit error correction is this. It can be obtained similarly, and the cost of the circuit for phase error correction is 44 and for bit error correction it is 160. So summing it up, actually we have this QECC that can correct up to 6 simultaneous phase errors, which is a huge thing, but it fails to correct in one particular setting of bit error, but it can detect there as well. But the interesting thing is, coming to this 9 qubit QECC and our proposed approximate QECC, we see that the cost of the circuit is reduced by more than 55% here, and the depth of the circuit is reduced by almost 70%. So that is a huge advantage or savings that we get in terms of implementing our quantum error correcting blocks. And using this conditional probability formula, we can show that if we consider a symmetric channel where the Pauli X, Y and Z, these errors are equally likely, so they occur with probability 1/3, then using this calculation, it can be shown that our AQECC can correct, so AQECC is approximate quantum error correcting code. So this AQECC can correct a single error with probability 0.75. However, there are some papers which have argued that a symmetric channel is not really what is seen in real life, but rather in real life we have asymmetry and phase error is much more likely than bit error. And we have taken in accordance with this paper that the phase error is 100 times more likely than bit error. And similarly, again, using this calculation, we can show that in such a scenario, we can correct a single error with almost perfection. So this is almost 1. And that is our results here. Thank you for your attention, for listening. And if you have any suggestions, any comments, anything, please feel free to reach out in one of these. Thank you.